Welcome to this explainer. Okay, today we're tackling a very specific, very real-world data challenge. We're going to take the NHS Provisional Secondary Care Medicines data, or SCMD for short, and we're going to transform it from messy, raw files into a sleek, highly queryable data warehouse. If you've ever dealt with millions of rows of supply data, you already know the foundation is literally everything. So, let's grab our hard hats and get to building. But, before we actually start laying bricks, we really have to ask a pretty provocative question. Why not just load all our data into one massive flat table? I mean, it's how the data arrives in a CSV or Parquet file, right? Why complicate things? Well, if you've ever tried to run a complex aggregation on a flat table that has 30 columns and millions of rows, you know exactly the pain I'm talking about here. Aspiring data engineers run into agonizingly slow query performance, wildly complex logic, and just nightmare updates when they rely on wide flat files. We absolutely need a better blueprint.
So here's our architectural blueprint for today. We'll be looking at flat tables versus star schemas, defining the SCMD grain, building out our dimensions and the fact table, engineering for operational resilience, and finally, handling future schema drift.
All right, let's kick things off with Section 1, flat tables versus star schemas. It's honestly like night and day between these two approaches. The wide flat table kind of encourages these naive, messy inserts. It bogs down your databases, and it makes writing query logic a massive headache. But a star schema, think of a star schema as a finely tuned engine specifically designed for online analytical processing, or OLAP workloads. By separating our numerical facts from our descriptive dimensions, we simplify our query logic, massively improve query performance, and we make aggregations an absolute breeze. It just leaves the clunky wide flat table in the dust.
Moving right along to Section 2, defining the SCMD grain. Okay, so what exactly is the grain? Well, the grain is the foundational level of detail that gets stored in a database fact table. And for our NHS secondary care medicines data, we are defining that grain explicitly as this: one row equals one trust, one medicine, and 1 month. That's it. It is a precise snapshot of aggregated monthly data.
Seriously, if you take one thing away from this explainer, make it this. Every schema decision should be checked against the grain. I literally cannot emphasize this enough. If you start trying to mix daily data with monthly data or patient-level data with trust-level data all in the same fact table, your analytics will instantly become meaningless. You'll just end up with duplicated, inflated records. We established this rule on day 1 and we stick to it.
Which brings us to Section 3, dimensions and the fact table. Let's actually map this NHS provisional SCMD data into our new schema.
We'll start with the points of our star, the surrounding dimension tables. These tables provide the descriptive attributes that let us slice and dice our facts from all sorts of different perspectives. We'll have dim trust, which holds details like the trust type, the region, and their unique ODS code. We'll build dim medicine to house the Dictionary of Medicines and Devices identifiers, so things like the VMP SNOMED Code, the product name, and the unit of measure. And of course, dim time, so we can easily filter by month, year, or financial year. These dimensions are basically the who, what, and when of our data.
And sitting right at the center of our newly built structure is the fact table itself. Notice how it perfectly respects our grain. We have our foreign keys linking out to trust, medicine, and time. And sitting right alongside those keys are our numerical measures, the total quantity issued and the indicative cost. Oh, and a quick but super crucial note on that cost. The source data specifically reminds us this is an indicative cost based on list prices. It is not the actual net cost hospitals pay because confidential discounts aren't published. That is vital context for literally anyone querying this table.
Actually, before we load a single row, let's talk about the messy reality of data engineering for a second. Upstream files often have typos. For example, in previous iterations of this dataset, the column for quantity was misspelled as TOTAL_QUANITY, completely missing the first T. If you just patch this downstream in your scripts, you carry a typo right into your beautiful new database. Correcting typos right at the source, reconciling those naming issues before they hit the database, prevents silent failures and ensures our schema stays totally pristine.
Okay, transitioning to Section 4, building for operational resilience. Because let's be honest, a beautiful database is absolutely useless if the nightly automated load fails midway and corrupts your data.
A really critical concept here is idempotency. I know, it's a big, clunky word, but it's actually a very simple idea. An operation is idempotent if it is safe to run twice.
Let's say your pipeline crashes at 3 a.m. because a server blips mid-write. Can your task scheduler just run it again without duplicating thousands of rows? If your load script produces identical row counts whether you run it once or you run it 10 times, congratulations. Your pipeline is idempotent. It is the ultimate safety net.
So how do we actually achieve this for our monthly snapshot of SCMD data? We use this really elegant delete and insert by partition pattern. Step 1. Delete the existing month's partition from the fact table. Step 2. Reinsert the new partition atomically, meaning all at once inside a single database transaction. We want to contrast this against those dangerous, naive row-by-row upserts. Since our grain is a full-month snapshot, there's never a situation where we want some rows from an old run mixed in with some rows from a new run. We wipe the slate clean for that month and write the fresh data. Simple, safe, and idempotent.
Then there's the other pillar of operational resilience, referential integrity. This is basically a strict promise, a contract, that every foreign key in your fact table resolves perfectly to a real existing row in your dimension tables. Look, if a fact row comes in with some unknown hospital ODS code, we definitely do not want to silently insert it. By setting parameters like pragma foreign underscore keys equals on in tools like SQLite, we effectively create a circuit breaker. It rejects bad rows immediately rather than polluting our entire warehouse.
And that leads us to our final section, Part 5, Handling Future Schema Drift. We have to prepare for contact with the real world because data structures change. They just do. Let's look at a very real example coming our way for this specific NHS dataset. The NHS BSA has announced that starting with the Provisional Data Model update for July 2026, the dataset is changing. Column names are updating. For instance, unit underscore of measure underscore name will become VMP UDFS unit underscore of measure underscore name. New columns are being added for unit doses. And crucially, SNOMED codes and measure identifiers will start being provided as string data types instead of numeric. This updated July 2026 data is expected to be released in September 2026. If our pipeline isn't prepared for the September release, those new string values are going to completely break it.
So, how do we actually stop this from wrecking our warehouse? We secure the perimeter of our database by setting up data quality gates. Before the load commits, we check the data. Has the row count drifted significantly? Has referential integrity been broken by a new data type? If so, we trigger a non-zero exit code. We stop the pipeline cold. We do not silently load bad data and just cross our fingers that someone notices later. We force an alert, investigate the schema drift, update our dimension logic to handle the new strings and column names, and only then do we let the pipeline proceed.
By combining a rigorously defined star schema, an idempotent load process, and strict data quality gates, you don't just have a database anymore. You have a reliable, automated infrastructure. So I'll leave you with this. Instead of spending 80% of your time fighting messy flat files and pipeline crashes, what hidden insights will you uncover now that your NHS medicines data is perfectly modeled and completely resilient? The data's ready. The architecture is sound. It's time to start asking the big questions. Thanks for joining me on this explainer, and happy building.